So the next speaker is Andrew Wang. He did his PhD at the University of Edinburgh, and he's also one of the co-founders of the Blur Labs, and also one of the developers of Deeplnverse. And yeah. And so he's going to give us an introduction to Deeplnverse, focused on image reconstruction.
Can you hear me at the back? That's okay. Okay. So I appreciate you're all fairly tired now, especially after seeing so many theorems and equations on the board as well. That scares me as well. So it's going to be a bit more of a light-hearted talk, talking about software and why you should be using open source software and thinking about open source software, whether you are AI research in AI for reconstruction, like most of us here who implement these experiments day to day in their own research. But even for example, for teaching, for example, when now lots of students or people in undergrad or even before that are, I would say like deep learning native. They've all heard of it. They're all like learning Python at home, and I like this kind of open source kind of Python first approach where we're not just thinking about science and math anymore, but actually thinking about software engineering and kind of opportunities where this kind of software is benefiting research. Another maybe way this might interest you as well is even if you're not in AI at all, maybe you're a physicist or you're even working in the hospitals, this kind of software, I think, I like to think that this gives you like an entry point into AI and entry point into using deep learning for image problems. Anyway, enough of an introduction. So as Julian had teased earlier, so Deeplnverse is a PyTorch library for imaging with deep learning. So it's general and it's modular. So the idea is that we are gathering communities from the AI machine learning side, but also from various different modalities in inverse problems. So you see, for example, like medical imaging, which we are here today, but also, for example, satellite imaging or microscopy or multispectral imaging and other fancy modalities. So that's kind of one module, so the kind of different modalities. And kind of on the other side, so these kind of modalities of simulation are for conditioning on operators, etc. And on the other side, we gather kind of the state-of-the-art AI reconstruction methods from across the literature, and we kind of stay afloat on top of this literature. So, for example, end-to-end, reconstruction networks, all the way starting from the UNet, and networks that people know very well across the different literatures. Classical optimization, and then kind of the model-based image reconstruction, and including deep learning in that, plug-and-play methods, all the way up to kind of what's the biggest exciting research now, for example, diffusion models, MCMC, things that I don't really understand. So I want to say a bit towards the bottom, so you can already get started very easily. You can install it very easily. In fact, we've spent a lot of time time making it as easy to use as possible, just from the motivations I said at the beginning of the talk. So even like Julian spent an hour of his time recording a YouTube video. We definitely need more help with the YouTube side, but this is a very easy way to get started if you want. We have a quick start tutorial, for example. So as I was alluding to, it's kind of three main points I see, and you may see otherwise. So first of all is accelerating the research. So there's kind of lots of different methods. There's lots of moving parts when you're implementing deep learning. So I know very little about diffusion models, but let's say I want to compare to diffusion models in my paper, which I have done. I can very easily just call that in a couple of lines of code. Secondly is quite a cool one. So there's lots of kind of new, I would say, imaging inverse problems which are wanting to use AI. So, I mean, we've seen a couple today, but even across different communities, and this lowers the bar because you don't have to start from scratch again and reinvent the UNet or reinvent insert method here. And finally, there's a reproducibility point, which was quite interesting with the discussions earlier, in that I mean, as researchers, we all know that it's very hard to reproduce the code if you don't trust every single moving part. and we kind of, yeah, we realized that, and that's kind of the motivation of having these common definitions and that are well tested, etc. And also, it's a good way to disseminate your research. I mean, it's quite cool to come here and speak about synergy in Synergy, because it's kind of a similar approach in that these learning methods should be available across communities. Like, for example, like neural networks that are proposed specific for pet reconstruction. You know, this is just a neural network. We've studied it in lots of different fields before. Even non-learning fields like the, you know, like the MLEM is just a, you know, Poisson maximum likelihood, and that's already been, you know, that's very well explored in the Poisson deconvolution literature. So that kind of, yeah, we benefit from that synergy. So as I said, we've spent a lot of time writing documentation. This means that you can get started very easily, and also, you know, it's a bit of a synergistic thing as well, and you can contribute as well. So lots of examples across the different parts of the library, user guide, and yeah, we spent a lot of time, maybe too much time on documentation, well tested, etc., etc. Okay, maybe just a very quick tour of the library. So we have, so as I said, from different modalities, and so for example, lots and lots of different kinds of blurring, especially for microscopy applications, MRI, multicoil, etc., CT, cone beam CT, 3D stuff, yeah, etc., etc. I mean, this is the purpose of tomorrow for those coming to the hackathon. We're very interested in emission tomography as well, which is very related. And we have quite a lot of things that, you know, are peripheral to physics. For example, blind physics, you know, the case where you want to differentiate through the physics to be able to learn parameters like the blur kernel, for example, that you don't already have. So as I said, models. So for example, the classical stuff, unrolled networks. I know my colleagues who are contributing have spent a lot of time doing this diffusion framework where you can have these moving parts. You know, sometimes when you read a diffusion models paper, it's quite daunting. There's lots of things going on, but actually it is a framework. You know, that you can split that into, for example, data fidelity terms, and you know, specific ODs, SDs, etc. Okay, and then some other things that sit at periphery around that. And you'll notice, obviously, this is a framework. There's a lot of gaps. It's relatively new still, and we're always looking for, you know, ways that you can contribute if you have your own data set. Yeah, I mean, that's kind of intuitive. So just as like a quick example of a workflow, for example, you know, you don't have to be using this for everything, and most people are not doing that. So for example, let's say you are, you've come up with a new imaging physics, new hardware, so you'd be doing that yourself, but then you pick an off-the-shelf reconstruction algorithm. Or for example, you've come up with a new neural network or a new data fidelity term for a diffusion sampling method, then you can do that yourself. Like, there's no problem in that, and then you pick an off-the-shelf simulation physics to test your method on. Or let's say you've scanned a new patient or something, and then you got your own data, and then you can test that. So in the interest of time, I won't actually go through the examples themselves. These are two kind of medical related examples we've just pushed like this morning, so it's very fresh. So this is an example using self-supervised learning. So that's from the training side with the MRI physics operator, and fine-tuning a neural network. You know, these are kind of state-of-the-art methods that we're implementing. Another example we just pushed this morning, which was quite cool, is this is raw data. So this is a real scan at 0.3 Tesla, and this is an example that you can run. This is whenever we push something, it runs on our servers in Lyon, I guess. So this is, you know, all of this stuff works out of the box because it's, you know, it's run through this kind of continuous integration pipelines. Yeah, Julian's already talked about this already, but just to mention, I mean, this kind of embodying this kind of bringing across different modalities in that, let's say you've come up with a new inverse problem, a new imaging modality. I mean, I think there's a colleague spoke to us and say they witnessed some kind of ramification of you know, where this is like a one-stop shop thing where you can like start using this today on your inverse problems. I want to spend a bit of time to talk about the community because that is the most important thing for the software development, because that ensures that we have different people with different expertise. So first of all, it's Deeplnverse is already used globally in quite surprising places, I guess, considering most of us are based in Europe. And the community of developers is international as well, across both academia and industry. We are organizing hackathons every year in different places. Actually, these two are in the same place, so that doesn't help. But we will have one later this year as well. If you're interested, please look out for that. But yeah, this is the kind of the idea where we want to continue this open source by including people from whether even you're new to get started. You know, we have like I think 80 open issues right now there. Maybe a quarter of them are kind of good first issues, you know, things which is like simple fixes that AI could definitely fix, but we want people to fix them because that's your entry point into, you know, starting to code with PyTorch or Python. And if you want to contribute, there's some quite clear documentation on how to do so. And finally, if you want to read more, we've got the JOS paper. And we've actually just got a mailing list now as well, where we're kind of discussing new features. It's hard to keep up to date with these things, especially if you don't check Discord like me. So you can join that, and that takes you to a Substack, and then we're just putting out new features. So just some new stuff that was from the past few months. There was this distributed framework, so if you've got like physics operating on huge images, for example, you can distribute this across processors, or blind inverse problems that I talked about. But yeah, lots of new stuff coming from the community. Right, I think that's it. Thank you.